Welcome back. Welcome to this online NPTEL certification course on the molecular rearrangement and reactive intermediates. So in the last class I was started talking about carbocation, and I talk about the carbocation stability. I talk about some of the fate of the carbocation. I talk about non-classical carbocation. Then I also talk about what will happen if you have a neighboring group which could have a lone pair, or could be a a pi bond or a sigma bond which can participate in the neighboring group. So today I am going to mostly focus on two important rearrangement reaction. One is going to be the Wagner-Marvin rearrangement, which I am going to show you here, and the other one is going to be the pinnacle rearrangement. So today I think before I start about this two different rearrangement, this pinnacle and this Wagner-Marvin, I am going to just go back to the last class. So there was an important problem I want to discuss, which sometimes comes into the exam. So let me start talking about this example first. So I am going to start talking about this example where you can see these particular compounds here I am showing here. It could be a trio or erythro. I am sure you are familiar with the trio erythro nomenclature in the stereochemistry. But the interesting part here is starting from this erythro compound with this 2s 3s compound, what is happening after going for the acidolysis using acetic acid, it end up forming a single enantiomer. But once the reaction is happening, instead of erythro happening with trio, it giving a racemic mixture. Now the answer is why? Why in two different set we are ending up two different type of event? So in case of erythro, what is happening, once the first thing is in the acidolysis, now you can see this there is a pi electron cloud of this phenyl ring which is going to take part in the NGP now, this neighboring group participation. So now what is happening, this pi bond of this going to take part here, you can see this arrow here showing this leaving this OTS out. Now once this is happening, this pi bond is attacking here, it will generate a phenonium ion. So we end up making a phenonium ion here. Now once you make a phenonium ion here, there will be a positive charge here. Now your nucleophile can be attacking to this 3-member ring here. It can open up to neutralize the positive charge. It can also go for a resonance structure. It can make intermediate B here. So now the nucleophile can attack from this side and neutralize the charge. So now what is happening, it can attack from A or from B, but the interesting part is either it attack from A or B, it actually ending up making the same compound, same chiral compound here. But once you move to a trio compound, now you can see there starting from this trio 2 or 3s, in presence of acetic acid, again what is happening, this phenyl ring pi bond is participating in this reaction. It is giving this pi electron density, forming this phenonium ion. And now if you see, one of the important thing about this phenonium ion is, in this phenonium ion, if you think about this, the chirality of this phenonium ion is actually a achiral compound. If you see in my previous slide what I was discussing, this particular phenonium ion, there is only a C2 symmetry here, but there is no other symmetry element. But once you go to the next one, what we are finding out, there is a sigma plane passing through this. So that means this particular phenonium ion is achiral. So now what is happening, it can attack from this A, which I am showing here, and then neutralizing the charge, or it can attack through this B. So attacking from the A, it can generate one enantiomer. Attacking from the B, it can generate another enantiomer. And there is a 50-50 probability of attacking to both the positions. So there is a 50-50 possibility from attacking through the A through attacking through the B. So what is happening? It end up generating a racemic mixture. As it is generating two different enantiomer in 50-50, so which is making a racemic mixture. Okay. So I think there are several other problems which I am going to give you from this neighboring group effect, which I am going to give you during practice. So you might find some more example there. So now I am moving further. So I am going to start talking about the molecular rearrangement for the today's topic. So we want to start with this important rearrangement called Wagner-Marvin rearrangement. So this is a very important rearrangement reaction. So this is a very important reaction because this particular development of this type of cationic 1,2 shift, which I am going to discuss, actually applied in many different type of rearrangement. So Wagner actually at 1899, he published a paper where he shown that from isobornyl or from bornyl, in presence of acid it converts to camphene. So this was known before. Wagner actually brought into the picture that he found that this is going through a rearrangement. Okay, and then 20 years later of that discovery, Marvin also proposed the very same thing. So this is actually the beginning of this Wagner Marvin rearrangement. So there are a couple of important points. So this is of course a carbocationic rearrangement happening. So from here what you can see, there is a hydrogen, alkyl and aryl group migrates from one carbon to the neighboring carbon. So that is the important thing here, that the migration happening from one carbon to another carbon. And then we are going to also learn about the stereochemical things in the next slides. So before going further, let's try to understand how this conversion, what type of rearrangement is happening from conversion of this isobornyl to camphene. So what is happening in presence of acid? First thing is happening is the protonation. So once the protonation happen, it actually eliminate the water to generate this carbocation in the carbon 6. So now once it is generating a carbocation, if you try to draw this carbocation, that as there is a empty p orbital here, now you can see this sigma bond here can donate electron density to this empty orbital. So that will allow the breakage of this carbon 5 and 4 bond. So that will end up generating a carbocation in this carbon 5 position. Now if you try to just rotate that, you can write the same compound in this form. So now if you have a plus here, what it's doing actually, there is a proton abstraction happening here to generate this compound called camphene. So this is the rearrangement what Wagner actually proposed. And now we are going to find out some other example of this reaction. So we have learned about SN to SN1 reaction, but if you think about this particular example of neopentyl iodide. So in neopentyl iodide, although there is a primary CH2 is there, but this is a very bad substrate for SN2 reaction, because your backside attack of a nucleophile is getting hindered because of this 3-methyl group. At the same time, here if you try to go for a SN1 reaction, then it is also getting, it's not a very good substrate for SN1 because it is generating again a primary carbocation. So what is happening if you treat with silver nitrate and water? The silver nitrate is going to activate this carbon iodine bond to generate this 1 degree carbocation. I am sure you understand this part. And now once it is forming this primary carbocation, now there is a 1,2 shift happening from this position to this position. Again the sigma bond of this carbon and methyl is giving electron density to this empty p orbital of this carbocation. So that is actually generating a more stable 3 degree carbocation. As you guys know, the 3 degree carbocation is more stable. Now what is happening? Now it can capture water to come to the corresponding alcohol, or there could be a proton abstraction can happen which can go to the corresponding olefin. So it end up giving a two products in this reaction. So now we try to understand about this 1,2 shift, because this 1,2 shift you are going to not only see in this Wagner-Marvin rearrangement, there are many other example or many other reaction also you are going to observe this. So what is happening in this? Let us try to understand. So one thing I think we should be clear in the mind that this 1,2 shift occurs with retention of configuration in the migrating group. So what is happening here, that suppose this is the sigma bond which is actually migrating here. So suppose this sigma bond has a chiral center attached here with a particular configuration. Now that configuration will remain intact in the product as well, because if you see the corresponding transient state, what is happening here, this sigma bond is giving electron density to forming some sort of a 3 carbon 2 electron bond here. You have a positive charge here, and now this going to shift it to this particular carbon. So now you can see this stereo information or this particular configuration actually remain intact in the product. And if we try to understand this reaction through this orbital description, what is happening here, we have a 3 orbitals and 2 electrons. So, it forming this type of bonding here. We can compare this to, I think we have previously we have learned the bonding of this allyl carbocation. You can compare this with this allyl carbocation. So, here you can see there, but we have only 2 electrons here. We can able to show them in we can able to show them also that there will be 3 different orbitals. So, there will be a psi 1, psi 2 and psi 3, and then you can see this, it is a bonding orbital here. So, you can see these 2 electrons will be in the bonding orbitals, okay. And also you can see in this 3 center 2 electron tangent state which I mentioned is actually this is a aromatic system. If you think about a cyclopropyl with a 2 electron and a carbocation, we have learned previously in the previous slide I talk about. So, this will generate a aromatic tangent state. So, this slide is another important thing we can bring here, that why this reaction, this migration is happening when there is a carbocation. What will happen if there is a carbon ion? Does the migration happen? No. If you have a carbon ion here, then this 1 to shift is not happening, because once you have a carbon ion, you have instead of 2 electron, now you have a 4 electron. So, there will be another 2 electron here. So, that will make the corresponding tangent state anti-aromatic, okay. So, that is the reason why you can see this 1 to shift happens only when there is a carbocation. So, now let us move further and go through some example here. So, we can see here in this particular example, we have a cyclobutane ring, and then there is a tertiary alcohol here which get protonated after elimination of water, generate this particular carbocation. You can see that this is already a tertiary carbocation, but what is happening here, it is actually migrating from tertiary carbocation to a secondary carbocation. By looking into it, you might think, sir, why that is going through a less stable carbocation. That is not the case. There is a ring strain here which is getting released here, and now trapping of the water can get to the corresponding alcohol. You can think about that after it comes to this, as I was telling you, it can also go for another important thing is 1 to methyl shift, because in this particular cases this is a secondary carbocation. Now, once the methyl group migrate here, it will generate a more stable tertiary carbocation, where there will be elimination of proton can happen, which can get to the corresponding proton. We will go for some more example. So, this is another example of a synthesis of natural product where the Wagner-Marvin rearrangement was utilized. You can see here from conversion of this compound to this compound, just looking into the bigger structure, you do not have to be scared. You just try to look for what changes happen from going from here to here. You can see at the beginning I have a 5, 4 and 6 member rings. Now I have, so there was 5, 4 and 6. Now it was 5, 5 and 6 here, okay. So, what happened? We can see a clear ring expansion happens, okay. So, let us try to understand what is happening here. First thing is the protonation, then after the elimination of water, it will generate this the more stable tertiary carbocation, and after forming this tertiary carbocation, what is happening? Now there is a 4-member ring attached here. So, this 4-member ring will try to get expanded to release the strain. It will go to this 5-member ring, forming this particular carbocation here. Now, once it is forming this carbocation, it can trap with water to this corresponding product. I try to draw this in this fashion also to give you an idea what is happening here. If you look into this particular carbocation, you can see there is an empty p orbital here, and now this is particular 4-member ring. Now you can see the sigma bond is now ready to give the electron density, okay. Let us move for some other example here. So, this is another example where we can see the first thing is happening is once you treat this compound with HBr, okay, first thing is going to form this corresponding secondary carbocation. So, you can think about the Markinov rule. I think we have learned about that. Is going to form the more stable carbocation here, but it is not the most stable, because now once you have a 1 to hydride shift, it can generate the more stable tertiary carbocation. So, once it forming a carbocation, you can see if there is a possibility by doing a 1-2 shift, it can form a more stable carbocation, then reaction follows that pathway. And now you can trap with this Br minus can be trapped to form the corresponding bromo product. Again, similar thing can happen here if you have a cyclo pentane ring with this vinyl group here that can get protonated to corresponding this carbocation. Again, here is the driving force is the ring expansion. So, in the previous case what we have seen a 1-2 hydride shift. Here what we are seeing, we are instead of 1-2 hydride shift, this is a ring expansion happening to make this secondary carbocation. Now, it is not going to stop here in the secondary. Now, there will be another 1-2 hydride shift going to happen. So, this is this after this 1-2 hydride shift, it will form the more stable tertiary carbocation which is going to form the corresponding product. So, these are what I am going to teach you in this throughout this journey, that we are learning different example. Not every cases there is a general rule cannot be followed, that always there will be hydride, always there will be alkyl. You have to try to understand what are the different stereoelectric effect, why the migration is happening. So, next example also about the ring expansion. So, starting from this alcohol, once we treat with HCl, it is going to protonate first, then there will be ring expansion happening to form this particular carbocation. As I said that ring expansion is a very important reaction, is release the strain, and then there will be a hydride abstraction happening from here which will generate the corresponding phenon 3, which is a stable compound. It can also take a Cl minus here to form some of this byproduct. Okay. So, let us try to go to this particular example here. What is happening here? First thing again, the protonation of this OH to generate this compound. Now water elimination is happening to generate this carbocation. So, now it is very interesting. Once it is coming to this particular carbocation, now things are interesting, because now there is couple of different possibility. One, it can go for this methyl shift, one it can go for this particular shift, because it can also, this sigma bond can also able to give electron density. But the problem is, if you do that, you end up generating a secondary carbocation. But here once you go for 1-2 methyl shift, you generate a more stable tertiary carbocation. Now, after that proton abstraction, we will able to give it to the more substituted olefin. So, moving further, there is another example here. So, these are the case of these Norbornell examples here. If you are able to treat this corresponding alcohol with HCl, is end up making a different product here. So, it is not just getting out from here and getting putting a Cl back there. It is not happening like that. So, first thing is the protonation, then elimination of water to get it to this particular carbocation. Now, there is a 1-2 shift happening. Again, there is two possibility. First thing, it can be 1-2 methyl shift, or it could be this bond going to get migrated, which we have shown here. So, what is the problem if you have a 1-2 methyl shift? If you have a 1-2 methyl shift, you end up making this bridgehead carbocation, guys. This is very difficult, because making this bridgehead position planar will be very difficult. So, that is why the bridgehead carbocation is not going to form. What you are going to end up seeing? You are going to end up seeing this sigma bond going to give electron density to form this carbocation here. Okay. So, you end up seeing this particular carbocation here. Now, we can write this in this form, and which is a tertiary carbocation which can take this Cl minus to form this particular product. Okay. So, moving further, we have also another example here where you have 3 cyclopentane ring using also there are 3 alcohols here. What is happening once you treat with HCl? First it is getting protonated and the water getting eliminated to form this. As soon as form this carbocation, there is a ring expansion is happening, which is the driving force here. So, ring expansion is happening to form this. Now, if you have this tertiary carbocation formation happening, now there will be a proton abstraction to form this double bond. Now, the next is this can get protonated to the corresponding, and it can eliminate the water, go for the next set of carbocation, then it will form this bond, and then it will continue and form a phenyl ring with 3 cyclohexyl ring fused into it. We can go for another example where there will be 5 cyclopropyl group here. So, there is 1, 2, 3, 4, 5. with this corresponding alcohol here. So this is a very interesting reaction because this is kind of a chain reaction. Once something trigger, it will continue. So what is happening? First step is formation of this carbocation after water elimination. Once this carbocation is formed, the cyclopropyl group is going to get migrate to release the strain to cyclobutane. And after this migration is happening, you can clearly see there will be a positive charge going to form here in this carbon, and that is happen, you form a positive charge. Now as soon as there is a positive charge and there is another cyclopropyl group, it will keep on doing this, keep on ring expansion. The next cyclopropyl is going to go for expansion, then the next cyclopropyl is going to go for expansion. So it will keep on expansion till it form this particular compound. So it's a very important thing that starting from this thing you can convert all these different cyclopropyl group to the cyclobutyl group. Then there is another important example here where if you treat alpha pinene with HCl. In general, if you look into this alpha pinene, you might say, sir, if I treat with this, it will go to the double bond, form this more stable carbocation, and then it will treat with Cl minus to form this corresponding chloride in this position. In this carbon, the chlorine will attached. But actually it is not happening. After this carbocation, although this is a tertiary carbocation, but there is a 1,2 shift happening from this. Why 1,2 shift is happening? Because you can see there is a 4-member ring here. This 4-member ring is going to get expanded to 5-member ring. So then it is, although it is making a secondary carbocation, but the driving force is the ring expansion, and then it will take the Cl minus to form this particular product. So you are not getting the chlorine here, which you thought at the beginning that it will form the chlorine here, but it is not. It is going to get further expanded to form this particular compound. Okay. So moving further, we are going to learn about the last example here, where we have a olefin here, which can get protonated with H plus to form this carbocation here, which is a tertiary. Then it is going to get migrate to form another tertiary carbocation here. Then, but this is happening very stereospecific manner. The methyl is also getting migrated to form this carbocation, which is finally getting trapped with this lone pair of this oxygen to form this compound. So you might see that I am talking about different example because again I told you at the beginning that this particular topic there are a lot of question comes in the exam. So you can able to prepare for exam as well. So now I am going to talk about another important example called pinacolone rearrangement. So before I go to the pinacolone rearrangement, I want to see what is called pinnacle. So these are vicinal 1,2 diols. Again, if I talk about vicinal 1,2 diol, you might think about the synthesis of using osmium tetroxide, dihydroxylation of olefin. But there are other methods you can able to make. You can starting from ketones using magnesium AgCl2. You can able to clip this single bond to make a diradical. I am going to discuss those reactions in the radical part. Then it can be have a formation of a dimer can able to make these corresponding pinnacles. But again in this method you can only make symmetric diols. So both sides will have a same group. So after making this, I think the next thing is if you treat with the acid, what will happen? So this reaction was discovered by Rudolf Fittig in 1860. So you can see how old this reaction is. So what is happening once you treat this pinnacle with acid? It is going to get protonate one of the alcohol to make, and then after water elimination it will generate this carbocation. Now you can think about this 1,2 shift which you have learned in this Wagner-Marvin rearrangement. So you will see there will be a 1,2 shift going to happen which is going to make this corresponding ketone. So what is happening? You started from a vicinal diol and you end up formation of a ketone. So there is couple of important thing about pinacolone, because if you see lot of textbook or in the different literature, people have sometime wrote them in a stepwise fashion, the reaction. That means what I am doing here, I am writing in a stepwise, that first there is protonation, water elimination, then 1,2 migration, then product, and somewhere you might find that people are writing this in a concerted mechanism. That means formation of the carbocation, formation of the migration, 1,2 migration, and then you are the water elimination kind of happening at the same time. But there are a lot of theoretical studies have actually done, and some of them suggested the reaction depending on the substrate can be stepwise or concerted. But if you use, one thing is they suggested that in presence of ionizing solvent, the reaction process through a concerted mechanism. So let's try to see some example here. As I said, this reaction is acid catalyst. So if I'm talking about acid, then there are two different class of acid we can say. One is protic acid, another is Lewis acid. So we can talk about using protic acid, this reaction can be done. Reaction can be done in terms of Lewis acid like BF3 threat, TMS triplet, magnesium bromide and others. Okay. So now we are going to go through some of these example and try to understand them. So let's go to the previous example real quick, and then I'll go to the next example. Suppose I have a diol which are symmetric, then there is no problem, there will be a protonation, water elimination, formation of carbocation, and as I told you, there will be a ring expansion happening from here to forming this particular product. And then if you treat this epoxide with a magnesium bromide, I told you during carbocation generation that if you treat epoxide with a Lewis acid, what will happen? It will generate this particular carbocation. But now if you see about this carbocation, now there is a 1,2 shift is happening here, at the same time this oxygen pulling this lone pair to forming this corresponding aldehyde. Now if you see, the problem is in the previous slide what I have talked about diol which are symmetrical. What will happen if they are unsymmetrical? What will be the things? Now if they are unsymmetrical here, in that case the first thing is where the protonation will be going to happen. Does it going to happen in this particular site or this particular site? That actually depend on the stability of the carbocation. If it is happening in this site, you can see this is also a 3 degree carbocation, but here it is 3 degree, there is 2 phenyl, it is a diphenylic. So there is 2 phenyl attached with this carbon. So that will make this carbocation more stable. So that will allow the formation of this particular carbocation, and then there will be a ring expansion. And also there is another thing, formation of carbocation, and the second thing is there is a ring expansion happening, that is also favor to get to this particular product. So let's go to some other example here. So now there is another thing happening here. We have one side we have a diphenyl and one side we have a phenyl ethyl. So by looking into it, you might say, sir, I have already learned in the previous slide that this carbocation will be favor. But the question comes, once you form this carbocation, now the question comes, which group is getting migrated? I didn't talk about that till now. You have a phenyl and ethyl. Who will be the winner? So what we find out that this is going to be the product where phenyl migration is going to be the better compared to the migration of ethyl. So now we have to try to understand what is happening here. Why phenyl is a better migrating group. Now if you try to understand in the reaction that there is this lone pair is coming here pushing this electron density, and then this particular group, suppose I put this here as a terbutyl. When this terbutyl group is migrating to this corresponding to in this carbocation, we have learned this in the Wagner Marwin shift, they will going to form some sort of a transition state where this migrating group, or if you say this RM or what, this migrating group will carry a delta positive charge on this carbon. And so that means that in the transient state there will be a things there where this migrating group will carry some delta positive charge, and the groups which can able to stabilize the positive charge more can be a better migrating group. That means if I try to compare between tertiary butyl group versus, so it will be better migrating group compared to isopropyl group. Okay, because that this is a tertiary carbocation will be more stable compared to a secondary carbocation. We have some other example here, and you can see that there is another important thing I am going to bring here, that is always not like that we will find somewhere and put a protonated diol. If you try to protonate this one, this particular vicinal diol, you make this carbocation. But the next thing is, might be thinking about it that okay, then the next thing will be, sir, I can clearly draw this, there will be phenyl migration will be favored, and I am going to end up getting this product. But that is not the thing is happening here. What is happening here? So we end up getting this as a product, because what is happening, if you think about it, the formation of this particular carbocation is not getting favored because you are trying to make a carbocation on the top of this cyclobutane. That means cyclobutanes are already strained molecule. Now you are trying to make it a carbocation on the cyclobutane. It is not going to get much favor here, because now what is going to happen, instead of that it is going to prefer to form some sort of a carbocation like this. Okay. So, if you form this type of carbocation, then you can observe this particular product here. Okay. We are not going to observe this particular product here. So, what is happening here? Instead of forming, instead of going for this carbocation here, first thing what is happening, there is a breakage of this bond. So, literally this bond is migrating from here to make a carbocation character after releasing of this water. So, after releasing of this water from here, it will migrate this sigma bond from here to generate a carbocation which is forming. So, here we have example where we have a cyclohexyl group here in the one side, another side with oxygen. Now, what is happening? Now, what will be the competition here? Of course, there will be this will be going to the more stable compared to this, because you have this oxygen lone pair can give electron density that will allow this 1,2 migration to form this particular product. And then there is another example here, we can get a protonation here very easily, but the problem is the migration. If you try to migrate here, so there will be migration of methyl versus phenyl. Now, if you migrate through phenyl, you end up making a very unstable strained molecule. So, that is why the methyl migration will be favored to give it to these corresponding products. And there is another example here, if you have two different size ring, as I told you before, there will be more possibility formation of positive charge on the bigger size ring compared to the smaller ring, because that will be more strain. That is why this product will be the major product. If you have a intramolecular case, it can also go through this type of expansion, it can release water, then there will be a 1,2 migration which will end up forming this particular product. Okay. And so, this is an example of a important molecule. Here you can see now you have a diol, both side you have a phenyl with 3 different methoxy or 1 methoxy 2 OH. In presence of BF3 etheride, it can form this carbocation. Now, there is a 1,2 migration is happening. You can clearly see this particular group will participate in 1,2 migration to form this particular product, and this can be further used to make this type of important bioactive compounds. So, in this class, what you have learned about the Wagner-Marwan rearrangement and Pinnacle rearrangement and several example of it. I hope you guys are like it, and if there are some references for here, you can follow, and thank you all, and thank you for coming to the class.